Hello class. In this video we're going to introduce the concept of limits, or at least an heuristic idea of what the limits is all about. In your textbook they use a physical concept in order to introduce the limit that is related with a physical problem, that is the average velocity and instantaneous velocity. But because really this example is quite didactic. So what I'm going to do here, I'm going to use the interactive part of your textbook in order to go through that example. Okay, so average velocity. What is the average velocity? Imagine that you are traveling from here to from Houston to Austin. Okay, and then your target is to have an idea of what is the velocity as far as you are approaching to Austin. So whenever you measure the distance between some intermediate point and your final target, that is Austin, okay, and you divide that measurement, that is distance, for the last times or by the last times, then what you are computing is the average velocity. That's the definition, okay? And you say, well, between San Marcos and Austin, the last time was, I don't know, 1 hour and a half, and the distance was 150 miles. So you made 150 miles divided by 1.5 hours, and then you have some velocity. Let's say that the number is 65 miles per hour. What that number is telling to you is that in average, assuming that you are following a straight path in your highway, in average, you were able to cover 65 miles per every hour that elapsed during your travel time. That's what this is telling to you. But today, with the introduction, we're going to see from the mathematical point of view what is the meaning of that average velocity. What is that number really? And for doing that, let me go to this interactive tool that we have in the textbook. Later on, if you have some curiosity how to display the interactive part of your textbook, I will show you how to do it. But let me start here with the portion of average velocity. So if you may click here, you're gonna open the average velocity that I already have opened here. Okay? So they define this problem. They say, well, assume that you have a rock, okay, that you launch in a vertical direction from the ground in a vertical direction, okay, and when you drop the rock, you drop the drop with an initial velocity of 96 feet per second, okay, and the formula that is going to give you the height of the rock as the travel time progress, okay, is going to be given by this quadratic equation. Okay, so as you can see, this is a quadratic equation. You can see here that the leading coefficient is negative. That's the reason that that quadratic equation is dipping in the hours duration, okay, and well, from there you're gonna compute the average velocity between two reference points in time. So for instance, let's say that as they say here, compute the average velocity between the elapsed time of 1 second and, let's say here, 3 seconds and 3 seconds, okay? So what you're gonna do, you are going to measure the height at 3 seconds, that is given by this formula, and then you're gonna measure the height at time equals to 1 second. You will make the difference, and then you will divide that difference by the elapsed time. The elapsed time is the difference between 3 seconds and 1 second, which is 2 seconds. And that is going to give you a number, okay? So let's put that one over there. So they say here, okay, so compute the average velocity, the part A at t equals to 1 second and t equals to 3 seconds. So you come here and you click over here and click over here. Okay, and then that is going to give you a number. Okay, so they got here, they say, well, the position at 3 seconds, is 144 feet. That's what you have over here. And the position at 1 second is 80 feet. That's the one that you have here. And the elapsed time, well, the elapsed time is the difference between the two times in which you are measuring the position. That is 3 seconds minus 1 second, which is 2 seconds. And when you make that ratio, you're gonna get 32 feet per second. So, what is the meaning of that? That they were able to cover around 32 feet per every second of travel time. That's what it's telling to you. But if you look here at this ratio, what really you are doing, and that is something that you learn from your courses of intermediate algebra, and then you retain that concept on college algebra, what you are really doing is that you are computing the slope of the line that is passing through these 2 points. And that line is what is called the secant line through those 2 points. And this is what you have over here. You see? Okay? So basically, from the mathematical point of view, the average velocity, that is a rate of change, is no more than the slope of the secant line between 2 given points. That's what you are doing. Okay? So let's for instance, to make some computations here. So this is the one that you compute for this one, for these 2 pairs. I mean, this pair here and this pair here. Okay, and they say, well, try to compute the average velocity of the rod over the interval 1 and 2 seconds. So now, instead of giving between 1 and 3 seconds, I want to see what happened between 1 and 2 seconds. So in 2 seconds, you can see that more or less your position is going to be around here. If your reference time is going to be this one, now you have another line, another secant line. And actually, that secant line, you can see, I haven't drawn that one yet, but you can see in here that the secant line have a slope that is a little bit higher. You can see from there. Okay, so what do you expect is to have a higher average velocity. Let's see what happened. So we come here and we check, okay, between the interval 1 and 2. So 1 and 2, and you can see now, that's what I was telling to you. You see, if you compare the previous one, that was this one, between 1 and 3 seconds, when you go to 1 and 2 seconds, the secant line, or the line between those 2 points, those 2 ordered pairs, okay, is going to be dipping into a higher value. It's steeper, okay? So, because it's steeper, what we expect? Well, we expect that the slope is gonna be higher. So the average velocity between 1 second and 2 seconds, what we expect is going to be higher than the previous one. Well, when we made that computation, that is this one here, is the position at 2 seconds, that is 128, minus the position at 1 second, that we know it was 80 feet, divided by 1, because it's the elapsed time between 1 second and 2 seconds, that is going to be 48 feet per second. You see, 48 feet per second is higher than the 32 feet per second that we had before. Because, of course, that line is steeper. So notice what is happening. So always we are building, taking or keeping this reference point that is 1 second. Always what we are doing is building another line that is steeper compared to the previous one. But the elapsed time is reducing. But it's reducing to where? It's reducing, look at here, before was between 1 and 3, then now is 1 and 2. What is common? The common is the reference time in 1. You see? So what we are doing, we are reducing the elapsed time around 1 second. What is going to happen in the limit when we have a very small interval between 1 second and something a little bit larger? That I'm going to build the second line between those 2 points in which the last time is very small. What is going to happen? That really what I'm going to get is the velocity at 1 second. But that velocity is not going to be an average velocity anymore. It's going to be the instantaneous velocity at 1 second. Look at here. So if I'm moving now to 2 seconds, it's going to be 48. You see? Now let's say, let's take here T0. Let's change the reference point. So first of all, we made the calculation between when we are in the ground and then the elapsed time is 3 seconds. Look at here, the second line and the average velocity, which is the slope of this one, is 48. Look at here when I reduce to 2 seconds, but I keep constant 0. You see, the line now is steeper, so we are expecting a higher average velocity, actually 64. And look at here, when I reduce the elapsed time to 1 second, between 0 and 1, I'm keeping 0. It's even higher, okay? At some moment, if I'm going to consider an interval in time that is a little bit higher than 0, but very close to 0, this is going to be the slope of the line that is passing through the point 0, that is the tangent, that is the instantaneous velocity. But the important point is that it's going to give you the idea that the secant or the slope of the secant approach the velocity instantaneously in some reference point when the elapsed time really is very, very, very small around that reference point, that in this case was 0. Okay, so let's go to there. So as I mentioned to you before, now we are going to compute the instantaneous velocity at some specific point. What is the meaning of that? Well, for instance, if you, in our example that I mentioned at the very beginning of this video, if you are traveling from Houston to Austin, so you want to know what is the instantaneous velocity at some specific point. Let's say Austin. When I arrive at Austin, what was the instantaneous velocity at that moment? Not between two neighbor points in time, just at that specific moment when I arrive to Austin, for instance. Okay, so what you're gonna see here is this axis that you see here is time, and they're gonna take as a reference point 1 second. And you can see these arrows over here. What these arrows is telling to you that now they are going to construct or build the average velocity between 1 second and some elapsed time after 1 second, but it's really close to 1 second. And they're gonna see, well, what happened if that elapsed time always is gonna becomes smaller around 1 second. What is gonna happen? Well, what is gonna happen is that in that ratio of the average velocity, we are going to approach, okay, the instantaneous velocity. We are going to approach a number that is going to be the instantaneous velocity at 1 second. And that is the heuristic idea of the limit. The limit is just to see how a function behaves around one point when you make the interval around that target point small and small and small and small each time. Okay, so let's see what happened. So for instance, in this table they have, well, the average velocity when the elapsed time, okay, goes from 1 second to 2 seconds. And you know that the average velocity, you know how to compute because we did that in the previous section. Now they keep 1 in all this measurement, but look at what is happening. They made the other point smaller and smaller anytime closer to 1. And they compute the average velocity for that particular point. Okay, from 1 to 1.5, then from 1 to 1.1, then from 1 to 1.01. See, they compute, for instance, in here, they compute the average velocity between two positions. The position of the rock in high at 1 second, and then 10 of the second after they launch the rock. You see? It's very small compared to this one. What we are doing? We are approaching what is the velocity at 1 second. That is called the instantaneous velocity. Now, they made the calculation for us already, and you can see that this is 48, 56, 64, 63, 63.98, 63.9984. So in the limit seems to be that it's going to be around 64 feet per second. Oh, per second? Yes, per second. Okay, that is the limit. Now, from the graphical point of view, what is the meaning of that? The meaning of that is that the slope of all those secant lines that you are building, when you are considering all these points, the slope is going to tend to a final number that seems to be is 64. But that final number, from the graphical point of view, what is going to be? It's going to be the slope of what? That's what we're going to see in the examples. So, first of all, let's see what happened with the last time, or the height. So between 1 and 2 seconds, well, this is the position in height. This is 128 feet, and the previous one was 80 feet. That was the difference of distance in the vertical. Okay? If I consider an interval of 1 second to 1.5, now this interval, this vertical distance is going to be lower, and so on. Anytime is going to be lower at the moment that this distance is approaching basically 80 feet. What is going to happen with the time? Let me see. Let me go to the next one. Oh, oops. Instantaneous velocity. This is two. Okay. This one over here. What happened with the slopes? Look at here. Let me, this is refreshing. Okay. So, for instance, if I have in 2.5, and I'm going to compute the average velocity between 1 second, okay, and 2.5 is the slope of this line. You see, now if I go to 2 seconds, between 1 and 2 seconds, the green is the slope of the second line. You can see that every time is approaching to that point, okay? If I'm going to 1.5, that I'm reducing now the height, but I approaching to 1 and make it smaller the slab times, you can see that the second line is almost parallel to this red line. What is this red line? This red line is the limit, okay? And this red line basically is going to be the tangent line in the point 180, in which the height is 80 and the elapsed time has been just 1 second. I mean, is the velocity at that specific time. Okay, so this red line, that is the tangent at this point, have a slope, and that slope is the limit that we compute before. Okay, you see that that slope is 64, and let me get the number in that table before. You see that as I was approaching 1, for very small amount of elapsed time, the slope was 63.9984. Okay, so what is the conclusion from this? That when you are making the elapsed time smaller, very close to the reference point in which I want to compute the velocity, in this case 1 second, okay, all the slopes of the second line, are going to have a limited slope that is going to be the slope in that reference point. The second line has to limit, in this exercise, the tangent line at that point, and the slope of the second line is going to tend into the limit to the slope of the tangent at that particular point. That's what is happening, and that's what is called the instantaneous velocity. Is the limit when the elapsed time goes to 1. And what is the meaning of the elapsed time goes to 1? That always I'm going to consider a very small interval around 1 and to compute the average velocity there. Then we record that slope, we consider even a smaller one, and so on, and you're going to see that at some point the values are going to be almost constant, it's not going to change. Well, that limit is the instantaneous velocity. And they put here this in a very nice way. So you can see, for instance, if you go to 2.5, this is the distance, 180 and 40 and between 140 feet and A, and the elapsed time goes from 1 second to 2.5 seconds. I mean, the elapsed time was 1.5, but when you have 2 seconds, now you see the new second, the slope, you know, that is higher. Okay, so this is the distance in height from 80 to 128, but now you can see that the time, the last time, is smaller. If we go back, look at here. If we go back to the previous one, the time is bigger. Now, here is smaller. If I'm going to 1.5, very small. Okay? And so on. So, you can see from here that this green curve approach or tends to move to the tangent curve that is in red here at this point 1. You see? And any time that the last time is going to be smaller, 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 this green curve is going to overlap the red one. But the red one is the tangent line at this particular point. And the slope is the limit. Okay? That is the instantaneous velocity, and that's what we try to use to give you the idea of the limits. Okay? Well, thank you.